used the big voice, you all settle down now. How's everyone doing today? Well, I want to praise you all for showing up here for the last session of a one-day event for some esoteric topic on what I presume tomorrow's a holiday, right? And then Friday's a holiday? How many people are working Friday? You suck. I'm trying to make a 4-day weekend joke. Everyone's like, I want to go to my 4-day weekend. And some of you have the audacity to go to work in the middle of a 4-day weekend. But anyhow, tomorrow's a holiday. You're still here, so thanks a lot. This talk is, as you can tell by the big screen, yeah, it's up there, is Understanding Probabilistic Data Structures with 112,092 UFO Sightings. Spoiler alert, this is mostly about the probabilistic data structures. The UFO sightings is what we in the business call bait. My name is Guy Royse. I'm a developer advocate at Redis. I like to joke that there are 3 things on this slide that matters. One of them matters to you, one of them matters to me, and one of them matters to my boss. My boss would like you to know that Redis is more than just a cache. It does lots of interesting things. Interesting things like probabilistic data structures, which you might not know are there. And so I'm going to show you all the theory and everything behind, well, maybe not the theory, but how these probabilistic data structures work. I'm going to show you a little tiny bit about how to use them with Redis. It's mostly about the data structures. I promise I won't sell too hard. But that's the thing that he cares about. I mean, frankly, I kind of care about it a little bit too, because, I mean, who doesn't want their options to turn into a big pile of money? You know, I do. That way I don't have to travel to Europe for a month. It's such a burden, you know. But that's what he cares about. The thing I care about on this slide, the thing that matters to me is that Twitter ID, perhaps not as much as it used to, but I still kind of am just narcissistic enough to want more followers, so give me a follow if you're so inclined, if you're still using Twitter. And the thing that you care about is, of course, the most important, is that GitHub URL right there, github.com/GuyRoyce. All the code and the slides and everything for this talk are out in GitHub in that repo, and I'll have a QR code at the end, so don't feel like you have to grab it right now. And I do want to humble brag here a little bit about, look at that domain name right there. I got guy.dev. And it works. All it does right now is redirect to guyroyce.com, but still, I've got it. So, 112,092. This is sort of a ridiculously large and precise number, or an accurate. We'll go with precise. I don't know how accurate this is. This is the number of UFO sightings that I have in a data set of UFO sightings gathered by the National UFO Research Center. I think that's the correct acronym, but it's the New Fork. And they have been accumulating these sightings of Bigfoot, not of Bigfoot. I have a different talk that I do where I use Bigfoot sightings, and I make a joke about how Bigfoot's my father. Little Polaroids of Bigfoot and me as a kid, you know. But this is the number of UFO sightings that are in this data set. And this wonderful man by the name of Tim Renner screen scraped all of this data off of their website and created a CSV file and put it up on data.world. And so kudos to Tim if you're watching. I always give him credit because I've gotten so much mileage out of his data sets. He's screen scraped Bigfoot data, he screen scraped UFOs data, he screen scraped haunted places, he screen scraped Dogman sightings. I don't even know what the hell Dogman is. Apparently it's a thing. He used all this data to do fun and ridiculous data science projects. For the UFO data, he was trying to figure out, he didn't really do any machine learning on it, but he did some basic analysis. And he found, for example, the most common, let's go with that one second. The most common location for a UFO sighting is within 50 miles of a United States Air Force base. Sounds legit? Definitely a UFO. Not the military at all. The other thing was the most common day for a UFO sighting in the United States. Any guess what the most common day would be? What was that? 4th of July. Independence Day. I just always picture these kids, this father and son sitting down to watch fireworks for the 4th of July. And he's like, Dad, is that a firework? No, son, that's a UFO. And so this data is delightful. It's fun to go spelunking through. And lots of good stuff in there. Tim found lots of really interesting things in that data. The Bigfoot data is equally fun. He discovered that if you look for Bigfoots, you'll probably find them in the woods. So it's just science. So, but the data itself is kind of basic in a way, but also very useful. In as much as this data can be useful, but it's fun to play with. We'll leave it at it's fun to play with. So each sighting has a summary, which is sort of just like an abbreviated version of, brief description of the sighting. And here we've got 3 saucer-shaped ships. Say that 3 times fast. High in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. That sounds like a UFO sighting to me. This took place in Salem, Oregon, and it's got a date time there in ISO 8601 format, saying it happened on September the 15th of 1950 at about 2 o'clock in the afternoon. We've got the shape of the UFO that was spotted. These were discs. You've got a duration. It's not a numeric value, it's like a textual description for humans to read. So this is like 15 minutes or a couple of hours, that kind of thing. We've got the URL that it happened on. You got the full text of the report, and we're going to play with this at the demo at the end, assuming I don't burn through all my time. And it's got the entire text of that eyewitness account and the latitude and longitude. So you can do a lot of fun stuff with this data. You could do like use geosets and figure out find me all the Bigfoot sightings in a radius and stuff like that. We're going to do different stuff with this data. We're going to do probabilistic things. So the important question here, when I say we're going to use this data with probabilistic data structures, is what the heck's a probabilistic data structure? So who here has heard of probabilistic data structures before? Show of hands. 2 of you. Who's used them? 1 of you. Good job. Get up here, you give the talk. So, and honestly, you probably all should have raised your hand because you've all heard of probabilistic data structures because I just told you about them. Don't feel bad if you don't know what these things are. I did a quick developer survey online when I put this talk together a couple of years ago. And if you look at this, this layout here, 58%, roughly 3/5 said never heard of them. Don't know what they are. 1/5 had heard the term, and like I said, I suspect that it was in the question itself. And the other 1/5 was split pretty evenly between having used them or knowing what they are. And so if you don't know what they are, you're like everyone else, no problem. That's why we're here. So, but understand what probabilistic data structures are. I want to talk first about their evil opposite, their evil twin, the reptilian to their gray, the deterministic data structures. Deterministic data structures are the data structures that you've been using all along. They do what you tell them to. You put something in them, and it stays there, and you ask for it out, and it pulls it out. These are our lists and our sets and our arrays and our graphs, our tables and our queues and our trees. These are the data structures that we use when we code all the time. If you are a .NET developer, you're doing C#, these are your dictionaries and your array lists. If you're a Java developer, these are your maps and your hashes and those things. And we pick these data structures in our code for lots of different reasons. And sometimes it's their capabilities, sometimes it's their performance. And I'm going to dive into one data structure in particular. I'm going to dive into hash tables and talk about how hash tables work. Now, some of you probably have computer science degrees, probably most of you, or at least half of you. I'm not going to embarrass you by making you tell me. And you may have taken a data structures class in college. And so if you have, hash tables will be review for you. But for those of you who haven't, it helps you understand, it's useful to know in general. But the principles, the way hash tables work, are they're very reflective in the way that probabilistic data structures work. It uses similar techniques. And so a hash table, this is a hash table. Thank you for attending my TED Talk. It's the key value store thing. We use them all the time. If you're in .NET, it's a dictionary. If you're in Java, it's a map. If you're in JavaScript, it's just every damn thing that's in that programming language is a map, is a hash map. Actually, I think in Java, they're not hash map. No, it's arrays are actually hash maps even. Because the arrays are just hash maps with the number as the index or something crazy like that. But anyhow, it's just a key value pair. And the way they work is they hash your key, and then you use it to populate a series of linked lists. And I want to talk briefly about what I mean by hashing, because we've probably all heard of hashing before. We've you hash your data and it turns it into a number. So here we've got a really simple example, sort of a block diagram of what a hashing function does. It takes some data here, those UTF bytes representing the name Scully, because I can't not have an X-Files reference and to talk about UFOs, and some sort of seed, and this function will turn it into a number. And it doesn't matter if you're giving it 6 bytes of data or 6 gigs of data, it'll compact it down one way to a number. And for a hash table, the hashing function you use is going to be an efficient hash, something that's fast. Like lots of times when I mention hashing functions, people say, you mean like SHA or MD5, which we don't use anymore. I'm like, well, yes, but no, because SHA is a cryptographic hash. Its purpose is to generate unpredictable changes in your hash number when you make small changes to your number, to your input data. And so it does that effectively. It makes it hard to guess what the values was when you see a hash, but it also makes it slow. We're talking about simple hash functions, like you could probably get away with using CRC16 to do this, honestly. But in my examples that I have in GitHub, we're not going to go into them, but I used a murmur hash. And I actually don't know how to implement a murmur hash. I implemented it by importing a node library. So that's how you implement a node hash. But the whole point of the hashing function is to take that data and sort of give you a signature or a thumbprint that uniquely identifies it. And if you give it the same data and the same seed, you will always get the same result. It's deterministic. And then a hash table, hang on, I think my earpiece is falling off here. We don't want to have a microphone malfunction. You use these hashing functions to hash the keys of your hash table. So a hash table consists of an array, and it's an array of linked lists. And you pick a size arbitrarily when you create it. So usually you just create a new hash and it does it magically behind the scenes. But the size is picked. I'm using 10 here, 0 through 9. So I've got an array of 10 linked lists. And then I take the key of the thing that I want to add to the hash table. I run it through my hashing function with the seed, if I'm using that kind of hashing function. And then I modulus it with however wide my table is. So I've got 10 elements, so I modulate it with 10, and then I get a number from 0 to 9. That is the index that I use then to store the value, the key and the value for the city of Salem. And so I get a 1, I put it in position 1, I store city Salem. And if I add something else, I get a different number, I put it in a different linked list, but the key and the value go in there. I might run into a situation where the index is already used. In that case, I just add another item to the linked list. So this is why we're using linked lists instead of just like places to store things. And so this is how you add things to a hash table. And so you end up with this linked list. And eventually these linked lists get too long and the hash table gets slow, and you'll rearrange it and say, let's double the array and rehash everything and put everything back together. And it's a slow operation, but it happens every now and then. When you go to read this then, you just reverse this process. So if I want to read the city out of the hash table, I turn the city into this index, and then I walk the linked list until I find city. And that's sort of hash tables in 90 seconds. So when we pick these deterministic data structures like hash tables, we're often making trade-offs of time complexity and space complexity. So we can get something that's fast but wastes space, or we can get something that's very compact but is slow. I like to use the examples of arrays versus linked lists. An array, if you don't fill the whole thing up, it's a fixed size, and so it's got wasted space. But it's very fast. You can go straight to the thing that you care about. Random access of an array is very fast, O of 1. A linked list is very compact. It's only as long as it needs to be, and there's no wasted space. But in order to find things, you have to walk it, and so it's slow. And so you're making these trade-offs when you pick your deterministic data structures on time and space complexity. But this is a little bit of a false dichotomy, because lots of times we're just picking them because of their capabilities, right? We're often picking the array because we know our data is fixed. We pick the linked list because it can be dynamically sized. We pick a hash table because we want to use keys and values. Because array lists, you could put a key and a value in an array list and then walk it all the time. But why do that when you have a hash table? Hash table is more useful. And so this is a little bit of a false dichotomy. We pick our data structures for lots of different reasons. And for some capability trade-offs, not just trade-offs for time and space. And it turns out there's another interesting capability that we can trade off on, which is accuracy. So we can pick data structures that lie to us. But in exchange for lying to us, they are fast and they are small. And so, for example, you might have a data structure that you can add, say, I always like to use the username example because it's really straightforward. You need to find out if a username has been used before or not. Now, if you have 1,000 users, you can do select star from users where username equals, and if you get 0 rows, you can let them use the username. If you have 1 billion users, that doesn't work. And so a probabilistic data structure could allow you to get more improvement in how long it would take to run that query, and not store 1 billion usernames, which would be at least 1 gig by definition. And reduce that space and time down by several orders of magnitude. But sometimes it tells you a username's taken when it isn't, like 2% of the time. And that's a good trade-off. And part of us as developers, that makes us cringe, right? It's like it should always be right and truthful, and everything should be perfect and precise and glorious and beautiful. Probabilistic data structures are a little messy because they lie to you, but they help you scale. And so that's what it's about. And actually, we use these all the time. This wonderful picture of the Devil's Tower in Wyoming. I think it's in Wyoming. It's in the Badlands, regardless. Who here is old enough to have seen Close Encounters of the Third Kind? A few of you? Yeah. Anyone hungry for mashed potatoes and feeling like Richard Dreyfuss? So this picture here is actually incorrect. It's a JPEG. And if you look right, where is it at? Right there it is. That blue pixel right there, it's the wrong color. Because JPEGs lose data, right? You compress them down and they lose some of the data. It's a little bit lossy, but it still looks like the Devil's Tower in Wyoming. It's good enough. That's what you're using probabilistic data structures for. They're like JPEGs. We can think of our probabilistic data structures as sets that have unusual or peculiar properties. So, and by sets, I'm thinking like the Venn diagram set theory thing, right? All that Venn stuff that I didn't learn in school that I should have. And now I just know because of memes. And every set, of course, has the ability to add something to it. You have to be able to add to a set or it's not useful. But the other things you can do with a set are you can get the items of it, you can get all the members. You can say, is a member in there? You can union them, you can intersect and difference them. You can ask for a count to get the cardinality. And so probabilistic data structures tend to work like these, but they only let you ask certain questions or have a subset of these operations. And so maybe you can add and you can test for membership, but you can't get the members. Or maybe you can add and then you can get how many unique items are added to it, but you don't know what those items are. So you can use them for things like counting and uniqueness and things like that. You can do things, you can build probabilistic data structures that are focused around membership. Is this thing in the set or not? Balloon filter works like this. We'll talk about that here real soon. You can look at cardinality. How many unique things have I added to the set? So if I add a star, a square, a circle, and a triangle, even if I added them multiple times, how many unique items are there? 4. Some are around frequency, where they're like a sorted set, where they will count the unique items. So if you add the star 5 times, you can ask it 5, and how many times has the star been added to this, and it will tell you. Probabilistically, it may lie sometimes, but it'll be accurate enough. Some do ranking, which is like frequency, but they don't keep an accurate count at all. It's very inaccurate, but they keep the relative order of them. So you know that these are the top 5 most likely probabilistic data structures to be featured on a clickbait article. And so that's another one. And with some of these sets, you can do tricks where you compare them. You get a similarity and say, how similar is this set to this set, even though you've lost some of the data. So they can do lots of things. These are lots of things that we need to do in our coding. And when it comes to probabilistic data structures, there are a lot of choices out there. Here's a few that I've listed. The ones that are highlighted in blue are the ones I'm going to be talking about today. So we're going to talk about Bloom filters, heavy keepers, and min hash, not in that order. If you notice there's a little red dagger on some of those, that means that it's part of Redis stack, which is a particular flavor of Redis that has these data structures built into it, and a bunch of other data structures like JSON and stuff that are fantastic. And if they got the double dagger, which is hyperlog log, that's part of open source vanilla Redis. And then there's a bunch here you can look at. And I'm not going to read through all of them, but these are the ones we're going to talk about today, just these three. I mentioned Redis stack, and so I'm going to insert my advertisement here. Redis stack is the regular good old open source Redis that you've been using if you're a Redis user since like the last 10 years, with extra capabilities added, including JSON documents, search capabilities, a graph database, a time series database, and Redis Bloom, which provides probabilistic data structures. So if you want to play with some of these on Redis, you will need Redis stack, which is totally free. And that's where you get it. So let's talk about Bloom filters first. Now, I'm tearing through my time like something terrible, so we got 23 minutes. Hopefully we can get through all these and see the demo. I may start going a little fast. So Bloom filters they're good entry-level probabilistic data structures. They're fairly straightforward. They're not too hard to understand, and you can understand how they work and why they work. A Bloom filter is a set that only allows you to check membership. So you can add things to it, and you can then say, is this thing in the set or not? A Bloom filter will say, no, it is definitely not in the set, or it will say, probably it's in the set. Not yes, probably. Bloom filters have a fixed size when you create them, and if you make them too small, they will get super American and be upbeat and think everything's awesome and say yes all the time. But they're stupid, stupid fast. Every operation on a Bloom filter is O of 1, no matter how many things you put into it. You can put 1 billion items in a Bloom filter, and it still operates just as fast as if it were empty. Which sounds magical and impossible, doesn't it? Let's see how they work. So Bloom filter's got a couple of different parts. You've got some hashing functions. Remember those? With seeds. I've got 3 here because it fits on my screen. You might have more, you might have less, depending on what you're doing. Probably not less. And you've got a bit array of a fixed width. I implemented this in JavaScript, and so I just used an array of Booleans, which is horribly inefficient. But in reality, you would probably do this like in C, and you would just have a block of memory and do a bunch of bit twiddling to set the individual bits. But you've got this bit array of fixed width, you've got these hash functions with seeds. And when you want to add something to a Bloom filter, what you do is you pass in that data and run it through the hashing functions. This is what we're building here is sort of have we seen this UFO sighting before? This is Megatron in the bushes. It's probably my favorite out of the ones that I've read. Megatron in the bushes is this great story of these guys who are they're driving down the desert highway, I think in New Mexico or Arizona, I can't remember, somewhere in the American Southwest. And they have to pull over to the side of the road to deal with a necessary bodily function. And so one of them gets out to take care of this bodily function, and they go over to a bush, to go behind a bush to do their business. And then they hear what they described as Megatron from the Transformers cartoon in the 80s transforming, that sound, right? Did I get that right? Yeah. That's my best trick all day. Yeah. The only other trick I have in my repertoire is I can laugh like Scooby-Doo. We'll see if I can, hang on. And that's all I got. Thank you for hanging on. So anyhow, so they stop to go take a leak, right? And then they hear the sound that freaks them out. And I'm sure they totally weren't high or drunk. And so they hop in their car and take off running, and these lights come up from behind the mountains and chase them down the road for like 50 or 60 miles. And they're, freaking out. And yeah, it's just a gloriously weird story. Megatron in the bushes is the title of it. So we want to know if we've seen the Megatron in the bushes story before in our balloon filter. So we're going to add it to the balloon filter because we've received it for the first time. We can check it later and see if it was added. So what happens when we add it to the balloon filter? Well, we run it through these hash functions. We get a number, because that's what hash functions do. We modulate that with the width of the balloon filter, and we get an index. And in each index, well, we've got bits at each index, and there's really not that many things you can do with a bit, so we flip them. We don't flip them, we set them to high. We set them to 1. And so now we've got 3 indices that are set to 1. And when we go to read that balloon filter and say, is Megatron in the bushes something we've seen before, we go through that same process. We look at all the indices and say, are they all 1s? Are they all high? Clearly, they were all high, I mean, given the story and everything. But we check, and if they're all 1s, then we say, probably. If we get a 0 back in any of those, we say, no, definitely not. Because if no one has ever turned a bit high, then no one has added this data before. So we can know definitively that a thing has not been added. Now let's add something else to the balloon filter. Let's add another story. I seen a UFO when I was about 13 years old. Another great story. This is actually exactly as it was screen scraped from the data, the website. All uppercase, bad grammar, everything. It's original. This actually took place in my hometown of Columbus, Ohio. So it's extra funny for me. And in this case, we go through the same process, and we get numbers, and we get indices, and we go to flip bits. But one of those bits, this one up here, is already set to 1. But that's fine, because we can read and say, I seen a UFO, they all come back 1. And we can read Megatron in the bushes, and they all come back as 1. And so it says, yes, these are both probably in the balloon filter. And we've got a collision, but because we have multiple hashing functions, that collision doesn't impact, it doesn't sink it doesn't make the data less valid. And so this is how it works. But what can happen, remember I said that balloon filters fill up and they start lying to you all the time, is let's look at another one. Investigators from the Bigfoot Field Research Organization observed a glowing green-blue sphere. When we do the math here, every single location already has a bit set high. And so if we asked initially, before we added this, is this in the balloon filter, it would say probably. If we add it, it will still say probably, because it doesn't change the state of the balloon filter. And so this is why they're probabilistic, because like the order and everything, you put everything in, matters. It's deterministic in the sense that it's clockwork. But because I chose to do it in different orders, I get different results. And so we can't ever be sure whether a thing was added based on the state of the balloon filter, or if it just coincidentally lines up. And if we do add it, it still coincidentally lines up, and so it doesn't tell us anything. And so this is why it sometimes can lie to you, but it will never it can give you false positives, but it will never give you false negatives. There's a function to determine how many hashes you want and how wide you should make your balloon filter. There's online calculators. It's not as hard as it looks, but we're not going to go into the math, because who wants to do math? I don't, and I don't want to spend the time on it today. If you want to do balloon filters in Redis, there's a command. They all start with BF. This is bf.reserve. This sets up a balloon filter. Here I'm providing the key name. I'm giving it an error rate, an acceptable error rate. It'll go through those formulas and do the math for you. Here I'm saying I find I want only 0.5% of them to be false positives, and you give it a capacity for how many items you anticipate putting in it, and then it'll do the math and do it for you. If you want to add things, you can use the bf add command and just give it the key and the values. And here we've got the bf mad command as well, which does exactly the same thing. It's worth noting down here that Redis will tell you when you add something whether it has modified the state of the balloon filter. If you get a 0 back, it's seen it before. It knows it didn't change anything. And so you can actually just add things and know whether it's in there or not. So you can minimize your round trips. So it's a nice little feature. And there's an exist command, which you can use to check if something exists in a balloon filter. And it's got a regular version and a multi version. I love that it says Mexists. It always feels like Mexican extremists or something. Just kind of a funny sounding name. I like to pronounce our Redis commands. There's the set add command, which is sad. And there's the h incr by, which increments a value in a hash, and it's hinkerb. And so they're all pronounceable. It's a little hobby that we have on the developer relations team at Redis. But that's really about all there is to using a Bloom filter in Redis. So let's talk about the next data structure. We got about 15 minutes. We'll talk about min hash. We may not get through top K. That'll be okay. It'll be fine. I'd rather show the demo. So min hash is about determining set similarity between documents. It's a little more complex than a Bloom filter, but what it does is it allows you to compare two documents and see how similar they are. So maybe you wrote a term paper and you wrote a term paper, and your professor wants to see if you're cheating. And so he or she can do a calculation, determine how similar those documents are, doing set similarity. And so this is what min hash is for. At its simplest, set similarity is just uses a simple calculation called Jacquard similarity. Jacquard similarity is simply the ratio of the cardinality of the intersection to the union. Now that's a dense little sentence there, so let me pull it apart. So you count up the number of things in one set, in all here. So here we've got sets from Scalder and Molly, or is it Mulder and Scully? They're face swapped, so I'm confused. But these are the states in the United States where they've seen UFOs. So Scalder has seen them in California, Nevada, Oregon, Wyoming, New Mexico, and Ohio. Molly has seen them in Florida, Kansas, South Carolina, West Virginia, New Mexico, and Ohio. And so the intersection is New Mexico and Ohio. There are two things in the intersection. New Mexico is Area 51, Ohio is Hangar 18, and so this sounds like real UFO sightings to me. The total number of things in the union is, well, there's 10 of them, because that's just how many states are on the screen here. And so you just take the intersection number there, divide it by that, and you get these sets being 20% similar. So it's just a simple ratio. Not that hard to compute. And so you could do this to documents, right? You could take take your term paper and take your term paper, and we could just put them in sets, and we could compare all the words. And then what would it tell us? It would tell us that they were both written in Dutch or English, depending on what you wrote your term paper in. It wouldn't tell you because we're using the same words all the time. And so they would be very, very similar because the language is similar. And so there's a way to turn your words into sets that doesn't do that by using trigrams and then shingling them. The idea here is you grab 3 words and you add it to the set. And then you grab the next 3 words and the next 3 words, overlapping like shingles on a roof. And this will create a set that you can then compare. And so here we've got, we notice to our left, further off into the mountains, a bright glow. This is the Megatron in the bushes story. And then we can take these sets and compare them, just comparing the strings, and then get a different Jacquard similarity calculation. So we're doing the same calculation that we did earlier with the states, but now with trigrams in the document. This is kind of neat, but it's slow. Because it's very precise, but it's slow. And so how do we improve the speed of this? Well, we use what we call a min hash. What min hash does is it takes these sets and turns them into numbers, a set of numbers that acts like a signature for the document. And then you can compare the sets of numbers using Jacquard similarity instead. And so what you do is you've got some hashing functions, as many as you want. It makes sense, your problem. We're going to use 3, again, because it fits on the screen. And we take every single element in this set here, and we run it through this hashing function, and we get a list of numbers. We take the minimum hash value, the min hash, and we add it to our set. We do that for another hashing function and another hashing function. And now we've got a little signature that is numeric. And comparing those numbers is going to be a lot easier than comparing all those strings. And there's going to be fewer of them. Because you could take 1 gig of data or a paragraph or an entire paper and run through this and still get the same set of numbers. And then you do the same thing for Molly. And you get different numbers, but some overlap. And then you can do a Jacquard similarity calculation on those numbers instead. And then get the similarity of the documents. Now it's probabilistic, so it's not going to be as accurate, but it's a lot more performant. And you can save these off, and like if you had to compare every term paper that was written by all of you in this room and see who was cheating, that's a lot of comparisons. If we did that with strings, it's not going to scale. Since we've done it here with these signatures, though, we can compute that signature for each document and then compare them. That's a much more performant operation. And so that's what min hashes do. They let you compare documents. So pretty neat. We got 10 minutes, and we'll skip that slide here. We'll go through top K super quick. This will probably Well, hopefully you get it. It's building on these ideas of hashing your data, but the top K uses two components, actually. It uses a heavy keeper, which is what we're really going to talk about, and it uses a heap, a min heap. And basically, as you add things to the heavy keeper, it counts them. But sometimes you'll get collisions, and those countings will be eroded. But whenever it counts something, it gets a count. Whenever you add something, you get a count back, and it says, is this bigger than the value that's at the bottom of my heap? If it is, it puts it in there, and then you recalculate, you resort it. That's basically how it works. And this will give you rankings. It's good for like trending topics, because things that come through frequently but then fall off get eroded away. And things that are more common build up. And so you can use it for trending topics. You use it for network traffic analysis to see who's hacking you. There's a lot of uses for this. It's a little involved, but we all need to make top 5 lists, right? So I mentioned that it has 2 parts. A heavy keeper, internally, the way it works is you've got, it's in some ways kind of similar to the Bloom filter and in the hash table, in that you have a series of hash functions. And then each hash function has associated with it an array that is as wide as you want to make it. So the width of the heavy keeper is however many bytes you want to make it, or how many buckets you want to make it, and the depth is however many hashing functions you have. And in those buckets, each of those elements, you have a place for a hash value and a place for a count. A brand new one has these all set to 0. Everything's null and 0. When we go to add something to a heavy keeper, we take that string, we hash it, we get numbers. And what we do is we get an index, the same way we did with the hash table, the same way we did with the Bloom filter, and we go into there, and instead of just replacing a value or anything, we increment things. So here, on this first line here, we got 5062, value 2, and so we shove the hash value and the number there, the count. We increment the count by 1. And if we want to add it again, it goes through that process again, and it says, hey, I found something there already. It's not empty. Like back here, it says it's empty, so just take it. Here it says, well, there's something there, and it compares the hash functions and says, or the hash values, and the hash values are the same, so it says, that's me. I own that one. And so it increments it again. When you go to add something else, and when you query that, you just reverse the process and get the number out. Take the biggest number. When you add something that might conflict, so let's add light. We add light to the heavy keeper, and we get some indices. And here you see on the first 2 rows, right, it claimed some new spots that were unclaimed, so it just incremented by 1. But at the bottom, 1442 is in position 2. It has a conflict. So what do? Well, you might reduce it by 1. You might erode it away. And so you do a simple calculation to do that. You have a magic number for B, and you take that to, you exponent that with the negative of the count. So if you've got lots of things, this number is going to be small. Your probability is going to be small. If you've got a few things, your number is going to be big. That B is a magic number between 1 and about 1. So it's like just a little bit more than 1. And so you do the math. So here we got probability of decay is equal to 1.05, which is the magic number I picked, to the power of the count, which is 2, negative. And that computes out to 90.7% roughly. If I had 1 million items in there, this would be a much, much smaller number. And so you roll the dice. And if it decays, it decays, and if it doesn't, it doesn't. We're going to say it does decay. And so now this position here does not get taken over by 1352. It remains 1442, but it's been decayed. It's been eroded by 1 value. If it gets knocked all the way down to 0, it's knocked out of place and something else can swap in and take it. And then when you query, then you say, well, what do I get all my matches? And I get 1, 1, and not found. I take the max value, I get 1. For the other one, for object, I query, I get all the values, I get 2, 2, and 1. I take the max 1, it's 2. And so it's preserving this count. And while it's doing it, it's adding these things to the min heap. It updates the min heap every time. You can use this in Redis as well. There's a top k.reserve command. You give it a key name, how many items you want to be in the top k, decide how wide that structure is, you decide how tall that structure is, number of hashes, and you give it a decay value, which is the reciprocal of that 1.05 that I showed you earlier. You can say top_k.add to add things to it. You can say top_k.query to say, is this in the top k? And it'll say 1 for yes, 0 for no. You can say top_k.count and say, I want to get the count of how many teardrop-shaped UFO sightings there were. And it will tell you. It will interrogate the heavy keeper. This number will usually be wrong, but it will always be less than the actual number. And you can call top_k.list, which will give you the top k items from the mid-heap. And so that is top k. I've got a super quick demo. I think I've got time to do it. Do you want to see it? So what I've done is I've taken all the UFO sightings that I have, and I run the words in the UFO sightings, the title and the description and the shape, and I put them in top k data structures in Redis after running them through stop words to get rid of a, and the, and those sorts of things. Break them apart in the words, and then we can do a statistical analysis to find the most commonly used words in UFO sightings, which is to say we're going to count them. So let's go ahead and do that really quick. Okay, I've got here, so I've got two little things. I've got the Python, if I had to, it's better than when I type Python. Yeah. We'll do build.py. So build.py is going to start tearing through the CSV file that's in here any day now. There we go. And it's going to start adding things to the top k data structure in Redis. And if I go into Redis Insight here and look in my database, is that big enough and visible enough? So you see I got UFO shapes and UFO words. There's no good way to preview that, but I can go in here and say like top_k.list UFO shapes. Oh, run it again. There we go. And then it gives me the top 10 UFO shapes that it's found so far. If I run it again, they might change. I don't know if they did or not. But there's more. So this lets you do it from the command line. You can do this from any programming language you want, honestly, because it's Redis and there's a Redis client for everything. But I've got another one that creates a little app. And so let's say Python app.py. Now we're running a little Flask application on port 6001. And if I find my web browser and hit enter, you can see that this is just going out there and hitting Redis every couple seconds to update the value. And so we can see the top UFO shapes. People don't apparently know what the word shape means, because I'm pretty sure light is not a shape, and other is definitely not a shape. Unknown, that's another good shape. But we're seeing on the left the most common words, and on the right the most common shapes. So this is my fun and ridiculous statistical analysis of the UFO sightings. I don't think I've ever actually gotten all the way through the data set, because it's kind of slow. I mean, it can be fast. The way I've written it is slow, because if you look over here on the output, I'm spitting it out for us to see each time, and then I call Redis, and I spit it out, and I call Redis, and so this creates a lot of slowdown. But it's worth it for a demo because it makes it visual, so you can see it's actually doing things. This could tear through this data much, much faster. So that's my silly little demo. This code is out on GitHub. We've got 1 minute. So here's some resources. Go check them out. We have a Discord server at Redis, discord.gg/Redis. I'm on there answering questions when I'm not on the road. We've got free classes at university.redis.com. And we've got a, excuse me, you can get a free cloud version of Redis at redis.com/tryfree, or you can use the Docker image for Redis Stack, which is what I did because I don't need a network then for my talks. So code and slides are at this QR code here. You can totally trust it. It will never give you up, nor will it let you down. It does actually go to my GitHub repo. I'm thinking about building an app that is a Rickrolling app, but also takes you to the site. So it just like takes you to the link and embeds it in like a Rickroll, so that I can do both. But I just can't bring myself to Rickroll my audience, even though I want to. So, and that's what I've got. So thanks a lot. My name is Guy Royse, and have a good holiday weekend.